that I showed you earlier. And so cluster 1 and cluster 7, again, just two separate groups of users. And these two clusters had the highest rates of adoption of two-factor authentication across all of those clusters. So there's something. And then these, clusters 4 and 5, were the clusters that had the lowest across the board adoption of two-factor. And cluster 4 and 5, let me just go back for a second. So they're not the largest, but they're somewhat similarly sized, so that's kind of interesting as well. This is a really, I'm so sorry for the quality of this. This is really embarrassing. But there is also an extremely, extremely, extremely weak but positive correlation between whether someone pays us monthly, so has a non-zero average monthly payment, and whether they have some type of two-factor. You actually can't even see it on the projector because it's so slight, but it's there. So I feel like I'm on the right track. Okay, but ultimately, these results are still kind of imbalanced. So what am I going to do? And so to be clear, from this randomly sampled data, these were 10,000 user accounts. It shook out to be about, I think, 13,000 accounts that could log into these accounts. There's a chance that the actual target class wasn't even represented in this data. So there's a couple of ways to deal with this, with the imbalanced class issue. So one is oversampling. So this would be taking all normal users and and not so normal users, and basically creating copies of this not so normal, like these bad users, and inserting copies into a duplicate data set. So I would have the same or almost the same number of observations of the class that I'm really curious about and also just the normal user base. I could also do something where I undersample. So I could just cut this large normal user set and make it equivalent to the smaller, more interesting target set that I want to look into. I will say that I have a little bit of a hunch that this is probably going to work better, that oversampling will probably work better, just because I think giving whatever model a chance to see this much will probably help out a lot as far as giving extra visibility into kind of what these accounts look like and being able to recognize them. But I'm probably going to try this too, just because this whole thing is, in the spirit of just let's randomly try stuff. So I'll probably do that. And then I kind of want to, I've touched on the fact that this isn't finished. This is still where I stopped just there is essentially how far I've gotten in this research. So I want to talk about a couple of questions. I presented this to the data science folks at my organization a week or so ago. I got some really good questions, and I want to talk about those. So one of the big questions that I've gotten is, how are you going to evaluate the results of this, particularly given that you're using unsupervised learning? This is a really hard problem. Just like in general, across any domain, across any problem where you're using unsupervised, or using clustering. Clustering is unsupervised. But a lot of it really depends on why you're using unsupervised clustering techniques to begin with. I keep saying unsupervised clustering. Clustering is unsupervised. There's not really a type that's supervised. So it really depends on why you're using this method in the first place. And unfortunately, most techniques that allow you to evaluate, formally evaluate the success of a clustering model require access to some sort of ground truth, some sort of labeled data. And so that's kind of tough. I could generate some labeled data myself because going back to the whole idea of domain expertise, I think I have a good idea of what constitutes a fairly secure versus a not so secure account. But again, that kind of almost defeats the purpose of feeding it to a clustering model to begin with. So I'm not really sure. I think this is probably going to take some manual review. I think I'll probably have to go through and just look to see, do the clusters make sense? Which doesn't really sound super cool and advanced, but that's the reality of what I'm probably going to do. And then another common question I get is, what other models have you considered? So all the models that I talked about here are centroid-based clustering. And so I'm probably going to try dbScan or some sort of density-based clustering model at some point. Again, I'm probably going to throw a bunch of things at the wall and see what sticks, just because I'm really curious how this will shake out. And what I'd really like to do is eventually, long-term, put this data into a supervised model. Use this to train a supervised classifier. And I'll probably do something like look into a random forest or some other type of ensemble model. So, and I think this is really the crux of this whole thing, is what is the point of this and how does this actually fit into the defensive security program at MailChimp? Like, how does this fit into what you already have? So ultimately, my goal for this is to, at the simplest layer, if you are a high-risk account, if we deem you high risk or you're a security risk, maybe we don't let you fail at login so many times. Or maybe there are certain things around the perimeter of the account that we don't let you do quite as much as we would an account that we deem not so much of a security risk. And that's super broad, I realize that, but part of it's going to be figuring out what that looks like. But really what I want to do is provide a heuristic for my team and for our anti-abuse team and anyone else who touches this type of problem to focus monitoring efforts on accounts that really need it. Because we have millions and millions of users, and it's impossible to catch everything. So if I can help carve out these groups, so one of them would be these kind of the accounts that I showed on the left side of the spectrum earlier, if I can help provide attention on those and give a spotlight to those, then I feel like I'm doing something to help my team. And that's really what I want to do. And no, this isn't perfect at all. This is just one tiny piece of the puzzle that, security defensive security requires a layered approach. And this is just one more layer on top of other things that we are doing, that we will be doing, and that I hope will help both my team and other teams get to the important stuff quicker. So, thanks. And I think we definitely have time for questions, so I am up for that if anyone has any.
Just raise your hand if you want to give the mic. Get his hand first. We'll get to you right after.
So you looked at 2FA to see if there was anything special about it. Did you look at the other variables as well to see if there's special things about them, or not yet?
Yes. So I can't really share all of it, but yes, there are definitely other pieces as well. That was just an example.
And so it looks like you're using Jupyter Notebooks, and
yes.
That's been something that I think several of the speakers today have actually kind of demonstrated. So could you tell us a little bit about how Jupyter Notebooks have facilitated doing this kind of analysis for you?
Yeah, for sure. In fact, let me go back to one of the screenshots just as an example. So Jupyter Notebooks, if you've attended any of the talks in here today, you've probably seen some examples of this. But essentially, it's an interactive Python environment that allows you to break up your code into these neat little cells. And it provides kind of like a living document. You can reuse it. So I can plug in any type of other data set. Like I could just change what data this is and still run this analysis again. So it makes it really easy to continue to hand analyses off. It also has the nice benefit of I can create notebooks that have these types of visuals in them, along with Markdown and other types of text annotations, so that I can pass this off to my boss, and I can pass this off essentially to an executive with this kind of content in it. So yeah, interactive environment, but also one thing that I really like about it is that it makes it easy to share, that kind of stuff.
So did looking at either the medians or the prototypes or the means when you did your clustering give any insight as to what the clusters actually meant?
Yeah, so unfortunately, the way they kind of took shape was based on account attributes that could be found really evenly spread across different which doesn't, I realize that doesn't make sense, I'm not explaining that well. Yes, but it wasn't super helpful for discerning why an account would be in one bucket versus another, if that makes sense.
Can you talk about security education for the users? And I mean, is there an outcome of the research? Are you retraining users? Are you communicating with them? Changing the variables?
Yeah, so this is actually something I've been discussing with some folks very, very recently. We historically have been really careful about reaching out to users or suggesting proactive things, partly because, you know, let's say we decide we want to email everyone who doesn't have two-factor authentication on and be like, hey, lock your stuff up, like, what are you doing? That can also kind of have a different interpretation. People can think, they will see that and go, oh no, MailChimp sent a security thing, we're really concerned, this looks like it could, they might have been hacked, oh no. So there's a fine line, and we're still trying to decide where that line is. We're talking about it though, and I am fighting very much for us to be able to somehow talk to these users, all of these, and say, please do yourself a favor and turn on these types of security features that we offer. So yeah, it's a really hard, I mean, it's, you know, there's the whole like policy versus what we want, so yeah.
First of all, great talk. I love seeing machine learning applied to like data science problems in the security world. And it kind of brought up for me like this question of like, what is the dependent variable in this model? Like, it seems like you have a lot of independent variables about users and not a ton that the model would even be able to pick up on in terms of outcomes. And so maybe just to build on the previous question, like, do you have metadata about the kinds of outcomes you're interested in, or is that just not available? Or like, what are you hoping to see at the end of this model, aside from identifying user accounts that are anomalies?
Yeah, so ideally what I would do, and I didn't really get into this in the talk just because there was a lot to cover, we have a known data set of accounts that have been attacked and taken over. I know what those look like. And so those are things that I want to go back and be able to potentially feed to some of the future models and say, can you discern whether these are good or bad? One interesting, I'm sorry I'm like going on about this, but one interesting problem that we have is when an account is attacked or taken over or abused in some way, almost immediately we have a team that reaches out to that user to say, hey, something happened, you need to change your password, you need to turn on two-factor, you need to set up these notifications. And so it's great for the user, but it kind of is unfortunate for this research because what happens is we don't get a picture of what that attacked user looks like at the time of attack. So that's actually an initiative I'm working on with some of our data engineers right now to get those account snapshots so that we'll be able to have that source of, okay, this is what they looked like. So I hope that answers your question.
So a follow on to that. Over here.
Sorry.
No, you're good,
Sorry.
you're good. So it seems as though you would have two types of malicious users. So the first type is an account that wasn't malicious, where their account got hacked, taken over, and now is being used for nefarious activity. And then you'd have the other type of malicious user account that was set up with the premeditated idea to use that account maliciously. Did you find anything from the clustering that would help identify or correlate with the first, those premeditated ones, I'd call them?
Yes. So this is actually another thing that I am working on kind of in conjunction with this. This is completely different. So the way those accounts look, those accounts that are created to be bad, they're just garbage, they look different. There are specific things about them that unfortunately I can't go into here, but there are definitely things about them that they can be very easy to detect. And so I don't want to say that's an easier problem, but in some ways it can be, because, particularly if it's something automated, if we see bot signups or things like that. We have some methods in place to deal with that. But this is a little bit harder because, or at least it's hard in a different way. And we haven't really spent a lot of time on this particular piece of it, which is why I'm focusing on that. That's also another a really big vector though, for sure. Yeah.
So it sounds like this is something that you kind of you had the idea and then you kind of have learned and evolved your knowledge of it as you've researched it. What kind of tips would you have for other people that are in their organization and might want to try to apply that kind of, to learn how to apply data science to their own internal problems, starting from kind of the same position you were starting at and trying to kind of follow in your footsteps?
Yeah, so that's a really good question. So one thing I will say is that I think I've been very lucky because MailChimp encourages a culture of experimentation. And so if I do all of this and it turns out to be, we can't really use this in production, we can't really do anything with this, that's still okay because we've learned something. So I will say, I will put that out as a caveat, but I would say, think about your user base or think about, what questions keep you up at night? And is there a way to somehow start thinking analytically about this? And I realize it's a lot easier said than done, but thinking through the lens of an analyst or a data scientist, what types of data do you have available? What can you query easily? What can you get through? Get your hands on data. Even if it's, if it's in a Google Sheet, if it's in a spreadsheet, it doesn't matter. Start getting familiar with it. Because the only reason I knew to go to some of these things was because I lived in an analyst role for so long. I knew what the user account landscape looked like. So I would say get really familiar with that. And then just start playing with things, start getting your hands dirty. Don't be afraid. So much of this failed, but I learned a lot from it, so.
I'm sorry, but I don't know if this is covered earlier before I was able to get in. But when you're doing this work, did you discover that there was a gap in data, so you had to go back and add new data sources in order to be able to get the correct sort of information?
Yes. Sorry, I wasn't sure if you had a second part to your question. Yes, absolutely. So one of those situations was in going through the different models, realizing that I needed not just account security related data, I needed just normal, what does your account look like? How much do you pay us? How many users do you have? Other types of just account attributes. But there's one piece, so I touched on this just a minute or two ago. We don't have data around what an account looks like at the time of attack. And so those values they're not timestamped and stored, essentially. When a user turns on two-factor, that gets updated, but we don't necessarily timestamp that and say this is the history, this is the change log of when a user enabled these things. And so that's something that I'm working on right now with our data team to get that in, because that's been huge. That's actually created a whole lot of extra work for this because that's something that I don't have, that source of truth. So does that answer your question? Okay.
All right, well, if we have no other questions, let's give another round of applause. Thank you very much.
Thank you all so much. I appreciate it. Thank you. Thank you so much.
I'm going to give you an assist with this.
Thank you so much.
I see.
Got stuck on my zipper. Yep.
And then,
Oh, there we go.
thank you.
Thank you very much. Hey, thank you so much. Yeah? Yeah. Interesting. So when you say small, how small do you mean? Couple thousand or?
Yeah, I'd say maybe 1,000, 2,000.
Is there any way you can, so when I talked about the oversampling, this kind of situation, is there any way maybe you could create copies of the classes that you're interested in and maybe do something like that. That's kind of hacky, but that's the first thing that comes to my mind. I might try something like that. So, yeah, good luck. Good luck, yeah, absolutely.
So kind of a general understanding, what I took away from your answer was that we really need to create a stream of account changes, like
Yes.
what a Kafka event stream
Yes,
says.
yes, yes, exactly.
Okay.
Yes, we do.
Okay, so then the next question is there, other than the obvious ones that I can look at my data and figure out, but were there unobvious things, like for example, here's an obvious example, time zone kind of thing, right?
Yep.
Okay, so like, I didn't realize time zone would be a significant state of the capture kind of thing. But do you have any examples that unobvious stuff that
Test one.
but overall good?
Test one.
So
I still need a higher.
but I can't.
Test one. There we go.
Don't feel comfortable talking about them just because they are kind of integral to some of this. But there are definitely attributes to the account. So like once I kind of zoomed out, instead of just looking at security related features and zoomed out, I will say there are definitely account attributes that end up having, I think, a little more bearing on that than, so to your example, time zone. Like I said, I can't go into it a whole lot more than that, and I'm sorry, I wish I could. But yes.
How much alcohol did I have to buy?
I don't know, that's a dangerous question.
If you don't remember, did you breach security?
Oh, God. What's that? Sorry, say that one more time. So I don't recall off the top of my head. Yeah, so I feel like that's definitely where we are. Like, I've kind of been able to say, hey, this is important. I think we should try this. And I've been loud enough about it that, I think I need to get out of the way. I've been loud enough about it that I think people have been like, well, we either need to take her seriously or placate her, so she'll shut up. So that's kind of where that's gone. I think a lot of it is dependent on organization, though. Like, so much of it is. And, and whether this ever sees the light of production, I don't know. This is still literally just, in a Jupyter notebook in Git. So, yeah. So I've seen a ton of people do it internally, and that's kind of why I was interested in looking at it specifically user-facing, just because that was such a big problem we have. What's that? Yeah, exactly. No, I get it. We have to be careful because people will.
Sorry, I interrupted you.
No, you're good. Thank you.
I'm doing a dashboard in Splunk. Well, we've got a system in Splunk.
Yeah.
That we're aggregating risk events.
Okay.
I've got a multi-axis grading system.
Move out of the way so.
This is going to go in with that.
Yeah.
Sort of a way
like I have some math on my slides, and I really want to see how someone from like what's a good other common ground. Yeah, someone from common ground like interprets the formula. Yeah. So there's another talk going on right now where they're actually like hooking someone up to an equation and like doing some. That's what we're just talking about. Yeah, you're gonna go there. You're gonna see my talk. I think in the last 3 years, I've seen like one talk that was not a good talk. What talk was that? That had to have been a good talk. It was Matt Sweet's talk about lock picking as an exercise in what is it called? Cognitive something, but I can't think of the name of it now. No, it's basically like doing a related thing physically so you can understand something sexually. I just blew it like entirely. Yeah. Okay. But you're talking about teaching people about national security response. Yes, I think I remember seeing that talk. Yeah, it was great. It was like something like I think that was last year. Do you know if Gabe heard about the speaker request? Okay. Is he willing to do it? I feel like I'm not supposed to be talking about it. Okay. If he doesn't, it's okay. I think I even put in a thing if he doesn't, if he's not willing, it's okay. Were you here this morning? No. Well, I was for like some of the talks, like that's so. Yeah. So like Pablo was flexing that we like him. Oh yeah, like literally. Yeah. This was I don't know. Is he happier with mine or is it his? Definitely happier with mine. Oh really? Okay, that's great. Yeah. Yeah, yeah, that's fine. Did you tell them in the speaker ready room that you were doing that? Okay, good. Just judging by the proportion of people, they'll probably give you less questions.
Hi, my name is Gabriel Bassett. My voice is my passport. Verify me.
All right, good afternoon, everyone. Welcome back. This talk is on reducing inactionable alerts to the policy layer, presented by John Seymour. Before we begin, just have a few quick announcements. First off, we'd like to thank our sponsors, especially our Clear Critical sponsors, Dale Mail and Critical Staff, as well as our special sponsors, Amazon, BlackBerry, Paranoid. It's the support of our sponsors as well as our donors, volunteers that allow this event to happen. Now, this event is being live streamed, so we ask that as a courtesy for our speakers and for the audience that you check right now to make sure that your phone is set to silent. If you have any questions, please use the question microphone so that the YouTube live stream audience can hear your questions. Raise your hand and I'll be sure to bring over that microphone. Lastly, if you have any feedback about this talk or the speakers that are in this here today, in the chat entry for this talk. With that, we're going to begin. Please welcome John Seymour.
Awesome. Cool, cool. Can everybody hear me? Awesome. Hi, everyone. Welcome to my talk, Reducing Inactionable Alerts via Policy Layer. My name is John Seymour, aka Delta Zero, and I'm a lead data scientist at Salesforce, where I work on the detection and response team, performing machine learning on security logs to alert to new attacks, to improve our existing alerts and rules, and to find and make new contextual data for use in investigations. My goal here today is to inspire you to be creative in where you apply data science and machine learning techniques. A major impact can be had with very small amounts of effort. If you come out of here with a nagging feeling that machine learning would help you with somewhere it's not normally applied, then I'd call this talk a success. Right. So like a lot of good presentations, let's start with definitions. Oftentimes, humans analyzing model-generated alerts will throw an alert away immediately, right? And we found as we've deployed our models, there are two main reasons what we've seen how this happens. First, when there are issues with the data pipeline. So these are things like when necessary logs are missing, when parsers fail, when joins between host and network artifacts behave unexpectedly, when third-party information is bad or corrupted, when deployment inconsistencies throughout the fleet, when added contextual information like host names is wrong, when added contextual information is stale where it used to be right when it's wrong, when added contextual information is right in an unexpectedly way. This list goes on and on and on, right? Contrast this to like obvious false positives, where we mean the model is not able to capture the complexity of the instance, where the activity can easily be determined to be a low priority or a non-existent threat to the business, such as a model alerting on beaconing to a company-owned resource. Generally, we've seen these handled after the fact. A whitelist is added, which says simply, even if the rule or the model says this is bad, don't alert on it. You can think of whitelists as a simplistic example of a policy layer which addresses the two causes for inactionable alerts. In this talk, we'll demonstrate how even simple modeling improves upon whitelists, and further we'll argue how modeling whitelists separately from modeling suspicious events is actually a natural approach to the problem. So here are some reasonable examples for whitelisting we've seen in the past, right? For a large number of alerts generated, we don't actually care about if a connection is completely internal to the network. So for these, it might actually make sense to whitelist anything that where both the source and the destination are internal. Or we might only care about a connection attack that's successful, right? So we might think filtering alerts where the connection was ultimately unsuccessful, like maybe the firewall blocked the connection, we might think that's a good idea. Or another widespread use for whitelists is in filtering if the domain is obviously benign. So like take the top popular domains and just shove that as a whitelist and say don't alert on any of these things, right? And these are obviously common and widespread ideas, but whitelists create some unintended side effects down the road. They're extremely rigid. If a whitelisting rule matches an event, then the event is just completely discarded, even if the activity is extremely suspicious for other reasons. They're also challenging to maintain, right? If you've worked with whitelists, you've probably noticed issues with updating them, since each problem set tends to have different whitelisting requirements. For example, take an extremely loud attacker moving laterally through a network. You can't whitelist internal connections for that. Or take failed connections. They could be NX domains today, but future command and control instances where the malware just hasn't activated yet. Large number of these might also indicate an infected host or something like that. And benign domains. A major way to exfiltrate information is through standard services that are likely whitelisted. Not even considering the fact that domains aren't static and most popular domains, or out of popular domains, not all of them are always benign. So I bet that most of you in the room are thinking, okay, we'll just include those as features in our models. And that's definitely a reasonable position to take. But here are some reasons why you might actually want a separate policy layer, at least at first. Let's start easy. Whitelists are already accepted by human analysts, and stating this alert has whitelistable characteristics, but we think it's suspicious even given those, is actually still generally well received and useful information to the analyst. However, model-centric reasons exist for such a separation too. Google Rules of Machine Learning advocates for separating spam filtering and quality ranking in a policy layer, and that a quality ranking should focus on ranking content that's actually posted in good faith. The main idea behind that rule is that spammers, the adversaries in that context, will attempt to emulate high-quality posts. So features used to indicate high-quality posts today might actually be indicative of spam tomorrow. That concept of adversarial drift also applies here. And the independence of the two types of models actually really helps with tuning training frequency. We all know that adversaries adapt. They're likely to adapt faster than what makes a model an alert inactionable. Also, separation gives us generalizability, which allows for centralization, reducing code duplication. Most of these features will be present in a large number of rules and models that you use. So even if most models exclude some of these heuristics, you can still have one whitelist model which applies to a large number of rules or models. Another is good data is actually the limiting factor for model quality in the intrusion detection space a lot of the time. Separating actually reduces the problem space so that models don't have to learn both what's a good alert, what's likely to be thrown away, and what's actually suspicious at the same time. And that actually means you can label data for different tasks and be a lot more effective with your labeling. And then finally, some of our team's models have multiple consumers with contradicting preferences. These might actually be unsatisfiable if you try to push them into the detection model. So how do we actually enforce the heuristics commonly used to filter false positives in a better way? Well, here's a simple machine learning-based approach that we've deployed at scale for doing so. We actually combine these heuristics using a function which penalizes alerts where any such issues are found without completely filtering the behavior. Concretely, if we let X be a list of binary heuristics, which are commonly used to filter false positives, then let your policy score be some number between 0 and 1 raised to the count of how many of these heuristics are true for a given event. For example, if lambda is 0.5 and you have 2 issues surrounding the data, then your policy score would be 0.25, or if no issues are detected, your policy score would be 1. And we just reweight the alert by this value. Right, so this is a really, really simple approach, and it's also simple to integrate with the models. Actually integrating this score with rules and models is very straightforward. You just multiply the 2 different scores together. It also has a lot of other benefits, though. The model can be reused for many use cases. So even in instances where the heuristics conflict with the actual model generated, such as that exfil detection model using good domains, you can actually just reweight the final alerting threshold for the combined score. Another benefit is the model is completely unsupervised, requiring 0 effort to train. And the model requires very little data science background to actually understand, right? But perhaps most importantly, it allows you to aggregate all of your different heuristics in one place, which makes it much, much easier to maintain. But we know there's no free lunch when it comes to these sorts of things. So what do we actually lose when we're moving to this sort of model for whitelisting? Well, to start, the main change is that we're now allowing a small number of events through that we wouldn't previously. So there is definitely, by definition, going to be a non-zero number of false positives. We've mitigated this quite a bit through thresholding, but obviously some of the new alerts that you get are going to be true positives and some are going to be false positives. A piece of low-hanging fruit that you might think is that the model is actually very, very simplistic right now, right? You could, for example, train it on historical data, like previous case adjudications. That's definitely something we're looking into. But probably the primary drawback here is how the model handles repeated alerts. With whitelisting, you can completely negate an alert from being generated, but you can't do that here. You can reduce them by adding sort of features based on prior case adjudications, but that makes the model complex. You could also eliminate them by adding additional, hopefully temporary whitelists, but that brings us back to the initial whitelisting problem, and it reduces a lot of the impact of this approach. But here are the main issues that we're trying to improve upon this. First, again, the most obvious being supervised learning, which would allow us to more finely tune that policy layer. After that, we plan to try out different stacking methods, so using like the output of the policy model as a feature when training the suspiciousness model and trying different configurations for that. And then finally, we're trying to more formally incorporate the consumer preferences like we stated earlier, such as different outputs for threat intel versus our SOC, or for the different responders for risks, vulnerabilities, and policy violations. So that's actually all I had. Does anybody have any questions?
Hi, thank you. Quick question for you. One of the big problems that I've experienced in the past with trying to kind of work with ML systems in general is the problem of introspectability. And for, coming from an ops background and having been the person getting woken up at like 3 in the morning, nothing is worse than having something like sometimes tell you one thing and sometimes tell you another thing, and like you can't figure out what the hell's going on.
Yeah.
How have you dealt with, while working with your customers, like dealing with that kind of problem of not necessarily being able to introspect the system in a easy to understand way?
Yeah, that's definitely a great question. So for the actual whitelisting technique here, it's actually very easy to introspect, right? Because you actually have the values of the different variables. You know how many are set to 1, et cetera. You can just return those to the ops people. Adding in something like a supervised method or something like that, yeah, that would definitely obfuscate, for example, and would harm the introspectability, right? So for this, we have issues, for example, with our host name mapping, for example, IP host name mapping. And for those, we actually encode that into our policy layer by saying, okay, this is known to be faulty, IP host name mapper, right? And we can surface those to whoever's investigating the alert. Cool.
Oh, yes.
Hi. So to someone who is completely unaccustomed to ML in general, what strategy would you say is best for determining a proper lambda, and how would you really tune that appropriately?
Okay, so I would probably do it the same way we actually did it, which is start at just lambda equal 0.5. So that means for every extra alert that you generate, then you half basically the score, right? The output score. If you wanted to tune it further, you'd probably need actually to get data and collect data about how many alerts are good and how many are bad coming out of your system. And that's when you want to actually move to something like a supervised approach anyways to sort of tune sort of that lambda. You could also have, say, a different weight for every single feature if you did that technique, whereas here we only have a single lambda for efficiency.
Cool. Sort of related to that, did you, as maybe a middle ground, look at talking to the analysts and seeing what they thought about the different alert types and assigning different weights based on their feedback?
Yeah, so we did definitely talk to the analysts, and we did consider assigning different weights to each, different heuristic that's being true. The only issue with assigning weights here is basically that sort of explodes the dimensionality of the problem, right? Like you have a different weight for every feature, right? Whereas right now we only have one sort of parameter we're tweaking. And so we decided that basically if we did sort of attempt that route, we would wait until we actually had a collection of data that we could use to sort of label things as being, well generated or not, and then just go a supervised approach anyways.
So just to make sure I'm understanding right, each feature is or each element in a whitelist is going to be a feature in the policy layer?
Sort of. So, for example, if we have like a rule that says it's a domain that's in a whitelist, or we have a rule that says, okay, the host name is missing from this particular log, or we're missing the parent log, or things like that. Those are all rules that we would use as separate features in that.
So, do you have any thoughts on how to handle the model expanding as you come up with new heuristics, over time?
Yeah, so that's also comes back to the sort of supervised training approach. If you start something simple like this, like really simple, then you can sort of get a lot of those ideas out and know sort of a lot of the different rules that you have. Even so, I guess you're probably going after the idea that like even if you deploy a model today, then later down the road you're going to discover some new and actionable alert rule or something. Oh, okay. Well, I was going to say like we're kind of assuming here that the drift in terms of what makes an alert inactionable changes much more slowly than the suspiciousness sort of score. So adversaries adapt, but your system doesn't adapt that fast. Cool.
All right, well, if we have no more questions, let's give another round of applause. Thank you.
Awesome.
I think he left. He's not like actually pissed for saying that, right? Like, okay, cool. Because he dropped off his mic. He's assumed a new identity. Cool. Well, yeah, that's like that's most of my talks. I try to like get it to a point where other people can follow without like referring back to class. We were gonna keep. Would you like to give your talk here too? So I guess by the person standing closest to the podium.
Do you have your adapter?
Yeah, right here.
That's not, it hasn't worked yet with the Mac, so we'll try.
Oh, really?
Yeah.
Because the one I used over in the room over there was working.
What port did you use?
That one?
This one? Top or bottom?
Top. So let's see what we got.
I haven't seen these work yet on a Mac, so let's see. Okay. Cool. Good job. Nice. It takes prep for it, but it's quick enough.
It's okay. I definitely have those where I flip them over and it won't work.
Well, it's not working on Mac yet.
All right. I'm going to give you this mic. If you would put this in your pocket. So the mic is currently off. Turn it on at your will, but the mic is directly connected to the internet. So only put it on when you want to talk to the internet. But switch is on top.
All right, testing, testing.
Yep.
Okay, cool.
We're recording. This is going to be shooting. Still in live streaming.
Yep.
No pressure, but has fun.
Yeah, that's cool. I figured we want to wait till 6:30.
Yeah.
Yeah, I figured just in case anybody was wanting to come at that time.
Also, this hasn't been a problem yet, but I wanted to give the warning just in case. Don't cross the projector. Like, don't go to the other side of the projector.
Yeah. Okay. Or I could just go over there and just be out of the frame.
I mean, I could move to catch the problem is the feedback.
Yeah. Oh, okay.
It's sensitive to feedback for some reason, so.
Okay.
How do I change the news?
Just drop in.
So if you tell him that, he actually has to say that. Oh, really? But the no. The speaker gets to be introduced. The exact training, I think, is the speakers be introduced however they want. Yeah. Give it a name.
And if you have any questions, we ask that you use the audience mic so that our YouTube audience can hear you. If you have a question, just raise your hand, and I'll be sure to bring over the microphone for you. And lastly, if you have any comments or feedback about this talk or the speaker, there is a survey attached in the shed entry for this talk. And with that, let's begin. Please welcome Rob Brand.
All right, so last talk of the day. That means I get to go till, 8, 9, 10, whatever. Anyway, here's a quick overview of what I'm going to be talking about. So as I said, my name's Rob Brandon. Been working in the field for 20 plus years, largely in incident response and malware analysis. But I did my PhD with the University of Maryland in machine learning and deep learning applied to security problems. Currently work for the threat hunting team with Booz Allen Hamilton, Dark Labs. And semantic representations of machine code are really my jam. So kind of the thing, why even mess with this whole embedding thing? A lot of malware analysis and reverse engineering problems are basically similarity questions. As a incident responder or network defender, when somebody gives me a new binary and says like, hey, we think this was used in an attack, it'll usually take me about 20 seconds to say, okay, yep, this is definitely malware. So the really interesting question to me is always not so much is this malware, it's going to be, okay, how does this work? Is it ransomware? Is this some kind of remote access Trojan? And similarly, you've got the vulnerability discovery problem. I've got this new binary. Are there any vulnerable code paths in here? So one of the things I'm going to really care about there is, does it import libraries from other things? Does it have code that has vulnerabilities that we already know how to exploit? So once again, it's a similarity problem. A lot of the methods we have out there for measuring code similarity, things like bin diff, graph comparisons, those really don't scale to n number of binaries. Doing an n by n graph comparison is really not computationally feasible. And similarly, things like SD hash and SSDeep work for some things, but they don't really encode any semantic similarity data that you really want for doing these kind of tasks. So this is where we move to embeddings. What embeddings are, these are inspired by the concept of word embeddings in natural language processing, where you take your information, whether it's word, paragraphs, or whatever, and you move it into some kind of high-dimensional space where similar things are located similar to each other. So in this case, what the goal here is to take a function out of an executable binary and somehow learn a high-dimensional representation of it so that functions that do similar things are located right next to each other in the space. And that allows us to do things like, say, we've got 5 million functions, and we want to figure out which of those which the functions in our new binary are similar to those. We can use some kind of locality-based search, rather than having to do a linear search through the entire database that we have. And another interesting thing with this particular type of technique is a lot of problems in the machine learning space aren't really so much machine learning as they are representation learning. The real challenge is to figure out how can you come up with some representation of your data that you can then throw a linear regression on top of to get the answer. So when we look at function embeddings, there are kind of a couple of broad ways that we can look at classifying them. So one of the ways I've started to look at function embeddings is to look at how much feature engineering is required to build the function embedding. So we have some methods, such as the one that I created when I was in grad school, which require no feature engineering. They just take the raw data to generate your embedding. There are a few others that have come out over the last year that other people have come up with that use some more sophisticated domain knowledge in pre-processing when they're generating the embeddings. And this is really kind of a really new area of research. Like I said, I finished my PhD in 2017 in this area. And since then, just really over the past year, there have been other people that have come up with, kind of independently come up with the idea and come up with their own method to build embeddings. So really there hasn't been any kind of comparison as to, what kind of things are these embeddings learning? What methods should we be using to create code embeddings? So this is just a few of the methodologies that have come out over the past year or two. The generative RNNs is a method that I came up with. And so I presented this at a DEF CON AI Village last year. This particular method works off of just raw bytes. You don't need to disassemble the function. You don't need to do any kind of analysis of the function. When I was doing my initial work, I did do some normalization to take, say, API calls and normalize those out from being a sequence of bytes into some kind of hash. But the initial experiments I was working with show that there's no noticeable improvement. So I left that particular technique out of here. So basically what you do for these kind of embeddings are you take something called a character RNN, which attempts to generate new information based off of previous information it's seen. So kind of like what's shown in the diagram over there. You take your function, you show it to the network 1 byte at a time, and after each byte, the network tries to predict what the next byte it's going to see is. You give it feedback at the end of each training cycle, based off what it got right and got wrong. And at the end, you kind of have a network that has created its own internal representation of the particular machine code that it's been trained on. So kind of what you do with these embeddings are you take your trained network, you show it a sequence of bytes from the function, and at the end of that sequence, you just take the state of the network, and that's your embedding. So kind of the embedding is basically what does the, or what information did the network find useful in order to predict each byte in that function. So worm2vec is a slightly more complicated function or embedding method that was presented by Abay and Bruce at Camlist last year. And what he's doing here is he's extending the word2vec algorithm, which is largely used for natural language processing, and he's extending it to executable code. And now my particular interpretation of this is largely based off of a couple conversations with him and his slides, so there may be some subtle differences in the way I implemented versus the way he did, but I think I'm largely faithful to the methodology. So basically, any issues with it are definitely my fault, not his. But so as you can see, this is an example of some assembly code that's been normalized into the modeling format that he's doing. Registers are replaced from EBX, EDX, RAX, whatever, into just a token indicating that this is a register. Same way with memory accesses and dereferences. Those are just replaced with, this is a memory address, this is a dereference. One of the differences or challenges with this type of model is that this requires disassembling the code. And as many people working in the disassembly space will tell you, disassembly is still a far from solved problem. So as I'll show later, having to do that does lead to some potential issues when you're doing this kind of work. And this falls into what I would call like a moderate level of feature engineering. You need to do some disassembly, maybe replace a couple of tokens, but you aren't doing any significant code analysis. You're not trying to compute the call graph or anything like that. So the next method I'm going to discuss is called SAFE, self-attended function embeddings. Created by Luca Massarelli and another group. I believe they were based out of Italy. This is a little more complicated model than the previous two. But in a lot of ways, it's kind of more sophisticated version of worm2vec. And you can get the modeling code for this particular methodology at their GitHub site. But basically the way this model works is so the previous model, worm2vec, you basically do word2vec on each of the instructions, and then you take all the vectors for a function that were computed for each of the instructions, then you just add them together. And basically the concatenation of all of them gives you your vector. The difference between that and SAFE also takes each of the disassembled instructions. They have a slightly more complicated tokenization scheme where they're looking at what memory ranges was each memory access in and doing some other slightly more complicated stuff, but largely a very similar thing. And there is then as well using word2vec to compute a embedding for each instruction. But then they're feeding the sequence of instructions into a self-attentive recurrent neural network in order to compute the final embedding. So very similar to worm-to-vec, but a little more sophisticated. And this falls into what I would consider slightly more significant feature engineering. And finally, there's ASM-to-vec, which was presented last year at the Jailbreak Security Summit by Sophia D'Antoine. And this is probably the most complex embedding methodology that I've seen anybody attempt to use to date. She included a lot of compositional features besides just the compositional bytes of the function, such as its neighbors in the control flow graph, and a lot of other very computationally intensive and very domain-specific things into the embedding method that she was doing. Unfortunately, the code for this is not publicly available, and I wasn't able to figure out how to recreate it just from the data that's out there, so I wasn't able to include that in this particular experiment. So finally, kind of to the data set I was using, I really wanted to find a data set where you had some very easy to define classes that were going to be present in the data set, but I also wanted some code that was going to have some relation over time. So kind of a natural fit for this for me was the code base of the various BSD Unixes. So if you look kind of at the history of things, in 1992 you had 386 BSD. Year or so later, that got forked into NetBSD and FreeBSD. Then, back in '95, NetBSD got forked into OpenBSD. So we have this code base that had a similar start, a similar origin, 20 years ago or so, but that has evolved significantly in the years since. So trying to come up with some kind of, code similarity analysis, this looked like a really interesting corpus of code to take a look at. So what I ended up getting out of this data set was 222 binaries. Each one of the binaries was present in either bin or user bin across all 3 operating systems. So your LS, your SH, whatever other binaries had a common name. The FreeBSD binaries I compiled with -0 and -02. NetBSD and OpenBSD, I unfortunately was not able to get the make.conf files to work for changing the optimization flags from the default. And after a couple days of banging my head on that, I just kind of gave up. Additionally, I only used functions that were greater than 16 bytes because I really didn't want to have just a bunch of thunks in there that were, of course, those are all going to be the exact same code, and that's going to throw off a lot of similarity metrics. So basically, the criteria was only functions that are greater than 16 bytes and less than 2048 bytes were used. Mainly because anything over 2048 bytes is really just an outlier size-wise, and to keep it easy, I wanted to have some boundary there. The initial parsing of all the functions was done with Binary Ninja. So I used Binary Ninja to determine where the function boundaries were, and all of these were compiled with debug symbols, so it was, didn't have to do any significant work, and there wasn't the problem of how do you determine where a function begins and ends. So Binary Ninja was used to extract the binary code and the disassembly for all of the code, except for the safe model. So one of the things I really wanted to try out here was the safe group. They trained the model that they released on a selection of 64 binaries from Linux. So several user space library binaries from Linux. So the interesting thing here is, can you just release a model trained on one set of code that generates embeddings and still have those embeddings be comparable to embeddings that are trained using other code? And I got some really, really interesting results with that, as I'll show you in a few slides. But the other problem was SAFE uses Radare2 to embed or to disassemble the code that it feeds into their model. Unfortunately, Radare2 is not always the most reliable binary analysis system, so it broke on the trying to disassemble the majority of the functions that were passed. So the final data set out of those 49,000 functions, I ended up with about 19,000 functions that went into the model. So some of the parameters used to train the model, worm2vec, I trained that model for 40 epochs. The RNN model trained for 20 epochs. At that point, it had looked like it had largely stopped changing in perplexity. Safe model, I didn't train a new model simply because I wanted to see how well that generalized. And yes, I know that this is definitely an experiment where I'm throwing a lot of different things out there. And if I had, over the next few years, there's definitely a lot of interesting things to follow up and maybe get a little more rigor. But this is still, like I said, I still got some really interesting results out of this. And all the models used a dimensionality of 100. Whenever you're comparing any kind of embedding type of problem, you really want to make sure you use a constant dimensionality, because different dimensionalities are going to have different capacities for encoding data. So you really don't want to say, okay, we're going to test this one with 10 dimensions and this one with 1,000, because obviously the 1,000 dimensions can hold a lot more data than 10. The other thing is each data set used a different binary. So FreeBSD compiled with Clang 7.0.1, OpenBSD was built with Clang 6.0.1, and NetBSD was compiled with GCC 5.5.0. So as far as the class breakdown, FreeBSD-0 had significantly more functions, or was a significantly larger part of the data set. I think it's still not large enough for any data set imbalances to really cause issues, especially since most of the issues here are more with model generation rather than with classification. Another interesting thing, kind of as a side note, is that FreeBSD 02, both FreeBSDs came from the same source code. So there's obviously a lot of function inlining and other optimizations going on between -0 and -02, which is something to keep in mind when you're looking at trying to take two binaries and determine did they come from a similar code base. So one of the things I like to do whenever I'm doing any kind of unsupervised or cluster analysis is throw up kind of a cluster plot of the data that I'm looking at. So in this case, these are just basic scatter plots of the data set for each of the models. And just kind of looking at it off the bat, you can see there's some really interesting things just in the data from right here. You notice the safe plot, the classes are a lot more intermixed when projected down to 2 dimensions via t-SNE than the other two. You get kind of the cleanest separation within the RNN model. And the worm2vec is kind of similar to the safe model. And granted, in a lot of cases, you really don't get much more than some intuitive ideas of what kind of class separation you might have in the data and some pretty pictures for a presentation. But I've still found this to be a fairly useful technique. So kind of one of the main method I've come up with over the past couple of years for determining whether two embedding methods work as well is heavily inspired by natural language processing. So one of the main main ways of testing natural language embeddings are to take your embedding and see how well it works for determining what words are synonyms. So if you look at English and other languages, we've got plenty of lists out there that says, loves, likes, appreciates. Those are all similar words. They're all synonyms for each other, so they should show up in similar parts of the vector space. So with binary code, we really don't have that common knowledge, that common ground truth consistency of, well, we know that we should say, when we see these two functions, we should say that they're similar. And that's where I came up with the concept of a consistency. So basically, all that consistency means is that hard consistency is that if I take function f from set A, and I take that same function with embedding method B, those two, out of the entire data set, those two should be the nearest neighbor for each other. So it's basically saying that embedding, if I embed a function in safe, hard consistency with worm2vec would be that same function has the same nearest neighbor in worm2vec as it does in safe. So soft consistency just means that the nearest neighbor from, say, function f in safe is within the 10 nearest neighbors, or the n nearest neighbors of the same function in worm to vec for some value of n. And actually, I got some really good numbers on that. So you'll notice the consistency between the RNN methodology and worm to vec was basically non-existent. It's basically showed that there is no consistency there, but there was a very remarkable amount of consistency between the worm to vec method and the safe method. To the order of 43% of the functions had hard consistency. And then even with 10, which is honestly kind of a small number for n for the soft consistency, that still brought it up to about 68% consistent functions from one data set to another. So kind of the takeaway from here is that, at least for this experiment, models that had similar feature engineering ended up having similar levels of consistency with each other. And I thought that was very interesting because, simply adding a few vectors together is very different than creating a self-attentive network over the same set of vectors. So, kind of the very simpler model with the same featurization ended up learning the same stuff as the more complicated model. And one of the things I'm interested in trying later is upping the value of n in this experiment to see just how far that increases the consistency. Maybe try with an n of 100 or 20 and see how that changes things. So like I said, the data sets that trained on the same stuff tend to be consistent. Data sets trained on different models tend to be consistently inconsistent. The additional test I did, which was so common in natural language, is given a supervised learning task, how well does the embedding work? In this case, most of the times that I've tried this on code embeddings, it's been kind of a waste of time because all of the supervised data that we have ends up being trivially easy to model in pretty much every vector. So in this case, trying to determine, the supervised learning task was which data set did it come from? Is it a FreeBSD? Is it an OpenBSD? Is it a NetBSD? Every single embedding methodology got 99-point-something% on that. So in order to really exercise code embeddings, we need to try and come up with some more challenging tasks and data sets to maybe get some more useful comparisons. Because saying everything works great isn't necessarily the most useful thing to say. So kind of some of the conclusions and takeaways from this is tooling can definitely make things complicated. The reliance of safe on Redair definitely makes that particular methodology hard to just take off the shelf and put into use without doing some significant engineering to, say, maybe put a different disassembler on the front. So another thing was, even if consistency between models is poor, that doesn't mean that the embedding method is not going to work for your particular use case. As we saw, even though the two different embedding feature sets learn different things, they still worked equally well for what we needed to use them for at the end of the day. And so getting kind of up to where things were going with ASM to vec, features besides the compositional features of code are definitely somewhere that's ripe for research. There's a lot of really interesting things that we could be doing, say, with trying to incorporate the control flow graph and other features from the binary into the model. So one of the things I think would be interesting to do from this in the future, most of the work so far has, people have naturally looked at functions as being the best way to, or the best, kind of semantic block of code to measure things in. Because humans tend to look at things in terms of functions. But looking at things from the computer side, maybe looking at basic blocks would be easier. You know, and a basic block is just a section of code where you don't have any control flow changes. So that sidesteps a lot of the problems you have when you're doing program analysis, you know, as far as determining, you know, have we ended the function, or did we just jump somewhere else due to something else? You know, or is this just a piece of code that just has nothing but jumps in order to get around function analysis? So basic block embeddings, merge those together is definitely a really interesting area that I plan on taking this in the future. So other than that, there's my Twitter and email. Anybody have any questions?
Thanks. Awesome talk. This whole area is very much my jam, so I really enjoyed it. Thank you. So having said that, I'm now going to hit you with kind of a sneaky question. One of the things that's come up in looking at embeddings for natural language models is this question of bias. So I think most of us are familiar at this point with the notion that if you translate from Hungarian that doesn't have gendered pronouns, you get different gendered pronouns in English for nurse versus doctor. So to what extent do you think, based on sort of your experience with this, that that might be an issue going forward? Because obviously a lot of the code bases that we have available to us, be it from, you know, malware aggregation sites or large code bases or stuff like this, these are all skewed from sort of normal behavior. So if you get into actually using this for like reverse engineering, at that point, the quality of those embeddings and whether or not it's actually mapping to the right functionality might be biased by that data and might lead you sort of down the wrong path. So do you have any thoughts on that, or how it might be possible to correct
so I think that's definitely a very heavy potential area, but I think one of the key differences that we can leverage in terms of code as opposed to natural language is that ultimately we're not really looking at what's the semantic intent. We're looking at what did the compiler generate. So that's where that's one of the reasons that I think moving towards a basic block approach, where we're looking at how do we combine basic blocks and then derive meaning from those, can potentially help a lot of the issues with the data set bias, because a compiler is only going to generate so many basic blocks. Humans are only going to code so many different things before they put an if in there or some other thing that's going to cause a control flow change. So I think that's definitely one possible mitigation. But yeah, that's definitely a huge area of potential concern, and one that I don't have a good answer for.
Cool. So I have a question as well. Kind of similar, on the similar track. So have you looked at function embeddings when you've, say, injected like a single line or something into the function and seen whether the function embeddings would also be similar there too?
No, I haven't. That would be interesting to do.
I'm just reminded of a news post from last week for silence and malware classification.
Yeah.
So
yeah, no, that would be interesting. I think these should largely be robust against that particular type of technique, just because the code that you inject would have to, in some fashion, overweigh the code that's already there. So I mean, if you look at the like say the worm safe model, you know, whatever line of code you're going to put in, first off you have to know what vector is going to be generated by the instruction vectorizer, and then that vector would have to be of high enough magnitude to throw off everything else that it's already seen. So that's, I don't know how, I think that's definitely interesting to do, but I think this would be fairly robust against that method for most functions.
All right, well then let's give another round of applause.
All right, thanks.